Hi, good morning. My name's Reaney. I'm in the Department of Geography. I always describe myself as a catchment hydrologist. I kind of work across data collection and kind of catchment simulation models, and done a lot of work around kind of reduced complexity, kind of simple, kind of more GIS-based approach. The work I'm going to present today is related to what we've been doing in Nepal around flood hazards and trying to think about them in a different way. This is where this has been supported by IHRR. There's also a NERC-funded PhD student, Callum Pearson, who's been closely involved in this work as well. So, in terms of our approach to considering floods and considering flood risk management, we try to break it down into kind of three distinct parts. Trying to understand the sources of flood water from the landscape, what pathways it takes, how does it move across the landscape, and the impacts, and where does that water end up, and how do we manage it at the point of impact. Now, traditionally, most work has happened at this impact end. That's your solid infrastructure, your concrete flood barriers. But actually, we're asking the questions around, well, what can you do to disrupt floods along the pathway, and also how do you change, how do you consider where the flood water comes from? So we're going to work through the modelling and the analysis we do across each of these different sections. So the sources is kind of been tied back to a new tool which we're kind of developing at the moment. We've kind of done a proof of concept on this called SCIMAP-Flood. Now, SCIMAP is, in the UK, it's a standard tool for diffuse pollution risk management. So if you want to know where sediment or pollutants are coming from a landscape, impacting water quality, SCIMAP is a tool which is used as standard. And that's a tool which was developed at Durham by, and I was part of the team, that was actually my first job when I came to Durham. But it kind of says, it takes this critical source area conception, where it says that you need a source, and you need a pathway, a connection, and when you get those two coinciding at one point in the landscape, that's going to lead to a problem. That means you can actually export the sediment or the flood water from that location. Now, that is how we think about sediment. But for floods, it's more complicated. You can kind of say, well, actually, flooding should be simpler. It's runoff generation, it's not runoff generation, and mobilisation of sediment and materials. But other things matter. So the timing of the flows across the landscape, how all that integrates together, is important. And also, it's only certain rainfall patterns or certain time series, like David was talking about there, certain temporal sequences of rain can have different impacts. And it's the same with the generation of floods. So it kind of comes down to being an index along these lines. So we say the generation is related to rapid runoff, which we're relating to land cover, the amount of rainfall, and the travel time across the landscape. So when we're talking about the travel times, we're really talking about where lots of water will accumulate together at the same time. If you think about all the travel times across the landscape, and think of that as a histogram, the modal area of that histogram is likely where the flood peak's coming from. And we can map that spatially onto the landscape. So we can start to say, these are the locations. But there's not just one point of impact in the landscape. If you go through and calculate this for one town at the bottom of the catchment, actually, and then you put in mitigation works to slow the flow, to reduce the flood peak at that location, you can actually increase the flood peak somewhere else. So we need to balance it out across different points of impact across the landscape. That might be a town, a community, it might be kind of critical infrastructure, so in terms of transport, or say kind of a power station or water treatment works. So we integrate all this together, and we can start to put together maps that look like this. So this is the East Rapti catchment in Nepal, and for kind of context, this is the Nepal-India border, this is Chitwan National Park, and about on the blinds there is Kathmandu. Now, what this map's saying is these areas highlighted in blue is where we calculate is the highest potential for flood waters to be generated. So to a certain extent across this mountain range here, and potentially across this area down here. But we've got this kind of key question, is this right? This is something which we can calculate in GIS, it's based on a set of logical assumptions, but we need to calibrate this to observe data. So what we did earlier this year was work with the flood impact patterns from the monsoon 2017 flood, And we're undertaking two phases on this. The first of these was an extensive mapping of over about 100 kilometres of the river to look at the flood cross sections, the size of the flood impacts, and that was in January this year. Phase 2 was an intensive campaign which happened in May this year, and that looked in the channel. We'll come on to that in a second. So, if you're going to cover 100 kilometres of river in Nepal, when you've not got too much time, there's one simple solution. Drones, so last year. Well, what you need is a proper helicopter. MAVs, not UAVs. But also, if you want to do drones in Nepal, you need about a year's notice. So, we chartered a helicopter, and by flying along the river channel areas, and using a photogrammetry approach called structure from motion, and taking about 9,000 images, we're then able to go through and build a 3D model, not just of these kind of upland areas, but also across the floodplain areas down at the bottom of the catchment, and we can then use that data in the modelling. So, only 7,000 images. We go through, we process them, and we can start to produce topographic data that looks like this. So this here is a 20 centimetre ground resolution DEM of the river channel, and we've got this for about 100 kilometres of the river channel. Of this, we can then start to pull off the cross sections and start to see actually, so that this cross section here, for example, kind of works across here. We can look at how wide the channel is, what the cross-sectional area was during the flood, and we can then go through, and this is from the campaign in January, they went out and did some detailed measurements on the ground. This is an ADCP boat. This is Matt Perks from Newcastle Uni, and this was working with Callum. And this went out and mapped the flow velocities in detail. So we've got an idea of the flow velocities, and the roughness, the cross-section size during the flood. What we can then do is actually start to work out what the peak discharge was for that event. Now then, using an approach called SCIMAP-Flood, what we're able to do is kind of calibrate that initial map to these observations and back calculate what all the land cover parameters should be and get a more detailed and refined map. So as I said, the next steps with this is this kind of calibration process. That's just what we're working through at the moment. And going forwards, we hope to expand this approach to other catchments, not just in Nepal, but other kind of mountainous regions or other catchments where this will work. And we're also planning, within some of this work in Nepal, to kind of focus in on some smaller catchments. So this is useful information. When this works, this should be a quick and rapid tool for people to use to say, look, if I'm going to go in and either say support farmers in certain locations to keep the infrastructure there, to keep that farming in those locations, to maintain that landscape, or if areas are going to get abandoned as kind of people move more to the city, which areas maybe you might want to reforest and which areas might you want to support, and how do you kind of manage that across the landscape. That's great, that kind of gives you that spatial targeting for mitigation. But what it doesn't give you is an idea saying, well, actually, if this change does happen, how does my hydrograph change? How does my flood peak change? So to do that, we kind of move on to the next tool. Now, so this is what we're using here, and is being applied to the same East Rapti catchment by Callum, is a catchment simulation model called CRUM3. Now, this is like a fully spatially distributed full physics model, and is able to put storms in, put climate change in, put changing land changes in, and see how the catchment hydrology will change, how the flood peaks may change. The cost to get that extra detail is approximately 1 million times more computation than the SCIMAP approach. So to do this, I think we've worked out it's going to take about a month to set the model up in the university computer cluster. That's fine if you've got a computer cluster. It's why there's the role for the SCIMAP approach as well as the fully distributed approach. So the kind of things it can give you is kind of detailed hydrographs, as I said, but with a certain amount of uncertainty. The shaded area there is the predictive uncertainty from the model. But you're able to get some very detailed spatial predictions as well. So if you take a DEM, this isn't Nepal, this is actually North Yorkshire, but you're able to go through, the model's able to output your spatial patterns of soil moisture and how that changes over time, where the flows are happening. So this is cumulative through flow through the soil. And you can then also look at the connectivity within the catchment and which areas are predicted to be most connected or not connected from the model. So this, in this case here, these blue areas is where, for this catchment, a lot of the water is being sourced from, as predicted. Well, as where the model predicts the flood water is being sourced from. So as I said, this is being applied at the moment, and what the output of this will be a set of detailed hydrographs of peaks in response to rainstorm, in response to changing land use and land management within the catchment. The final step is to say, well, actually, where does that flood water go? Who's that likely to affect, and how much damage is that likely to cause? How much damage is that likely to cause? So to do this, we kind of moved to the final set of modelling, which is inundation modelling, so like a 2D hydraulic flood model. This is able to give us detailed spatial patterns, but again, it does need detailed topographic data and building data, and that's the other thing we're going to be using the helicopter survey for early in the year to build a detailed model of the floodplain. For those areas, in terms of what's readily available, there's like 30-metre data from SRTM or ALOS. There are some more detailed kind of 5-metre, 1-metre data sets, but at a greater cost than it costs us to do the helicopter. So it did kind of work out. What is then the kind of predictions you can then make? This is just some initial runs that Callum did based on some 50-metre data. This is taking the whole river channel. So this is the whole kind of East Rapti. That's Chitwan National Park in there. This is the floodplain area here that the video was flying over. And you can start to predict for a defined hydrograph where you'll get deeper and shallower water and how it affects the communities which live in this floodplain area. 3 minutes. Okay. What we're going to be able to do is, for this area in here, is to take that kind of far more detailed data, and rather than running it at 50 metres, we'll run this at about a 1 metre resolution, and actually start to bring in the building data as well, and kind of classify the building data out from the ortho photo, like the aerial photo imagery, which we can build from the helicopter data, and from the topographic data as well. So really, what I'm trying to present here is like a 3-stage kind of like almost like a 3-stage increasing complexity set of modelling. The idea is that you have a tool which looks across a whole landscape, across the large catchments of thousands of kilometres squared, 5,000, 10,000 kilometres squared, to start to say, well, actually, where might you act? Or, and also, where might you look at it in more detail? There's then kind of more detailed catchment simulation models which can be applied in those areas, which cost more to run, but you want to make sure they're being applied in the right place to get the most information and most value. And finally, those kind of detailed flood inundation models then can say where that flood water is likely to go, and with those you can then bring in the structural engineering scenarios to see, well, actually, if we build certain size walls or certain retention areas within the floodplain areas, how much impact will that have on changing the flood pattern? As I said, this is kind of, a lot of this is being developed with Callum Pearson with his PhD, and we kind of work at the moment to get the SCIMAP-Flood approach kind of made available more widely. The SCIMAP for fine sediment and SCIMAP for microbial pollution are both available as web-based applications. You can go in and use it online with very little GIS or technical knowledge around geospatial data, and apply them. We're hoping to get SCIMAP-Flood to be in the same state. Okay.